Hello guys, let's continue our topic speaking about circles and its properties. In the last class, we've been talking about the area of a sector of a circle. So we know that the area of a circle, that the full circle is pi r squared, while when we are talking about the area of a sector, we have another formula to use. A equals b squared multiplied by the m, which is the angle, the central angle, over 360, which is the full circle. So basically I'm just taking a fraction, which is m over 360, out of the full area of a circle, which is pi r squared. I can use also, we said that I can use the radian measure instead of degrees. So instead of m in degrees, I can say m in radian, and 1 pi radian equal to 180. So instead of 360, I would use 2 pi. So this formula goes for both radian and degrees, but still we have a fraction of the full circle, which is the area in this case. We call this an area of a sector of a circle. We also took some examples how to find the area, and we said, for example, in this case, if it's 131, we can just take the angle, and r in this case is 12, and we can get the area of this sector. So now let's talk about another thing, which is instead of finding the area of one of these sectors, we have to find the length of this arc, which is the arc opposite to this central angle. Do you remember, guys, the circumference of a circle, which is 2 pi r? So if you want to find the full length of the circumference of a circle, we would say this circumference, this c, equals to 2 pi r. So if you want to find the fraction, which is the length of this arc, you would say, I would take again this angle, which is m, over the full angle, which is 360. So in case of finding the length of arc, I have to take the circumference, which is 2 pi r, and again m over 360, while the case in finding the area of a sector, instead of 2 pi r, I would say pi r squared. Still I have the same fraction, m over 360 in degrees, or again m in radian over 2 pi. It's up to you guys, you can choose radian or degree. It depends on the question. So let's take some examples about this. Okay guys, in this case, or in this question, we are asked to find the length of this arc, which is FG. Look at this, it's represent the arc, and he's saying the radius of this angle is 8, while the measure of the central angle opposite to this arc is 134. So guys, if you want to draw this angle, you would draw two radius, AF and EJ, and you would take this angle, this central angle, opposite this to this FG arc. So writing the angle in this case, we wrote the angle in front of the arc to represent that we need this arc, because you have two options to write the FG arc. You have this arc or FG. So in this case we have the central angle, which is 134 degrees. So how to find the length of this arc? Okay, let's try to use the formula for finding the length of this arc. Let's take another example. Again, in this case, we have the arc, which is GH. The central angle is 40. The radius is 6. So again, in the same way, we can find the length of this arc. Again, R equals 6, M equals 40. Doing the calculation, you will get the length of this arc. So area, length of this sector and arc. Okay, it's a simple way just to find the length or the area of any sector from the circle. Guys, speaking about circles and areas and arcs, we have some main definitions. Each one of these angles which has the central as a vertex of the angle and one of these arcs opposite to this angle, we call this angle a central angle. An angle, its vertex is the center of the circle. We call this arc AB the minor arc, while we call this AB again or ADB as the major arc. Why? Because we have the same central angle with these two arcs. But normally and most likely in any SAT question, when we are asked to find the length of one of these arcs, this indicates that we have to find the minor arc, which is immediately or opposite to the central angle. Another note, guys, for the SAT questions. Normally in SAT questions we have more than one angle inside the questions. As we said, if the vertex of this angle is the center of the circle, we call this a central angle. While if the vertex of this angle lies on the end points of the circle, we call this angle inscribed angle. In this case, look at this case, which is a very famous case in SAT questions. Normally, we have exactly the same figure in SAT questions. You have one arc, which is CD in this case, and we have two angles. The central angle, which is opposite to this arc, and we have the inscribed angle again, it's opposite to the same arc. So normally in SAT question, he would ask you this question. If the central angle, for example, is 100, find me this angle, which is the inscribed angle for the same arc. What would you do, guys? So immediately we can use the formula, which says the inscribed angle equals half of the central angle for the same minor arc or for the same intercepted arc. We don't care about the names, guys. Inside the question we care about how to find the numbers. So once and each time you see two angles, inscribed and central angles, opposite to the same arc, you would say this one is half of the central angle without any calculations, because they have the same opposite minor intercepted arc. Let's take an example about this. Look at this example, guys. In this figure, we are given one angle, and he's telling me find the measure of the angle POQ. So basically, he's asking me to find this central angle. Why we call this central? Because as we said, the vertex is the central of this circle. So we can note they have these two angles, they have the same arc, which is PQ. So I can say this angle is half of this angle, or this angle is twice this angle. So immediately I can say that this angle is 2 multiplied by this inscribed angle. So 62 multiplied by 2. So this angle would be 124. This is how we find the central angle or the inscribed angle opposite to the same arc. Thank you guys, hope you enjoyed the class.